I welcome you all to the first international conference organized by the Department of Biotechnology, Kamraj College of Engineering and Technology. The Earth is what we all have in common. The planet can live without humans, but human beings cannot live without Mother Earth. It's our primary duty to save our environment in order to survive in it. Therefore, sustainable development of the environment is the key factor to meet the needs of today without compromising the needs of tomorrow. Owing to this, the Department of Biotechnology has organized the International Conference on Sustainable Development in Energy and Environment.
Faith and prayer are both invisible, but they make impossible things possible. Now I invite CV Jemima Romola of MTech Biotechnology for the prayer song. Let us all rise for prayer.
இந்த காலத்திலும் இந்த நேரத்திலும் நன்றியால் உம்மை நான் போற்றுவேன். இறைவா உம்மை நான் போற்றுவேன், புகழ்வேன், இந்த வேளையிலும் போற்றுவேன். ஆதியும் நீரே, அந்தமும் நீரே, ஜோதியும் நீரே, என் சொந்தமும் நீரே. ஆதியும் நீரே, அந்தமும் நீரே, ஜோதியும் நீரே, என் சொந்தமும் நீரே. இந்த காலத்திலும் இந்த நேரத்திலும் நன்றியால் உம்மை நான் போற்றுவேன். இறைவா உம்மை நான் போற்றுவேன், புகழ்வேன், இந்த வேளையிலும் போற்றுவேன், இந்த வேளையிலும் போற்றுவேன்.
Light is the wisdom that vanishes ignorance. I would like to invite the dignitaries to light the Kutuvilaka. Thank you, everyone. Great teacher, empathize with students, respect them, and believe that each one has something special that can be built upon. I would like to invite one such teacher, Dr. I. Ganeshmurthy, Organizing Secretary of the International Conference, to welcome the gathering.
Good morning to one and all present here. It's a great honor and pleasure for me to welcome you all for the first international conference on sustainable development on energy and environment. Today, we will hear how our sustainable energy for all the initiative is maturing and bearing fruit. It is the golden thread that links poverty eradication, economic growth, and healthy environment. According to the World Health Organization, about 2 billion people still rely on traditional biomass for heating and cooking, and resulting the indoor air pollution is responsible for nearly 1.6 million deaths per year in the developing world. In addition, more than 1.6 billion people have no access to electricity. Our target should be the access of energy to all people in the world and the increase in global of improvement in energy efficiency. Distinguished guests, respected colleagues, ladies and gentlemen, now it is the time to successfully to wrap up 1.5 years work. Yes, it was started in the year of 2018 mid. Considering just how busy you all must be, thank you very much for taking your precious time to participate in the first international conference on energy and environment, sustainable development in energy and environment. In particular, I would like to extend my gratitude to our distinguished guests from abroad, University of Nottingham. First of all, please allow me to express my sincere welcome to Professor Sean Patrick Rigby, Director of Geoenergy Research Center, University of Nottingham, UK, for our conference. We welcome you, sir. And I would like to welcome our distinguished guest and expert, Professor N. Tajuddin, Professor and former head, Department of Microbiology, Bharathasan University, Tiruchirappalli, India. We welcome you, sir. Dr. R. Babu Rajendran, Professor and Head, Department of Environmental Biotechnology, Bharathasan University, Tiruchirappalli, India. We welcome you, sir. Dr. V. Sivasubramaniam, Professor and former Head, Department of Chemical Engineering, National Institute of Technology, Calicut, India. We welcome you, sir. Now, it's time for me to welcome our great expert and managing board members. I cordially invite our secretary, Mr. P. Magesh Kumar. I extend my sincere welcome to our joint secretary, Mr. VPP V. Periyasamy, and I welcome our treasurer, Mr. MSPRN Prasant Kumar. We welcome you all, sir. It gives me an immense pleasure to welcome our root, the principal, and one of the pillar of our college and coordinator of the conference, Professor Anant Acharya. We welcome you, sir. And I extend my heart welcome to the support system of our department and our lovable lady, Iron Lady, Dr. M. Vasanthi, head of the department, the convener of the conference, and vice principal of the college. We welcome you, ma'am. I'm very honored to welcome all the participants who made this conference functional and success. We welcome you all. I'm happy to welcome the organizing secretary, Dr. S. Karthik Kumar, Student coordinators, Mr. Carl J. Samuel of second year MTech, Mr. Manush Nandan, final year biotechnology, Ms. Shraddha, third year biotechnology, and Mr. Prasanna Kumar, second year biotechnology. Above all, I would like to extend my warm welcome to Dr. Professor Padanattam Badiyan, research consultant of our college, for his constant support and encouragement throughout the conference to be successful. Thank you, sir. Welcome you, sir. And last but not least, I welcome the blossoms, all the students of our department, teaching, non-teaching staff members for this August gathering. Thank you very much for the opportunity. I wish all the participants to have a fruitful time in this for the 3 days. Thank you very much.
Thank you, sir, for your warm words of welcome.
I would now like to invite our esteemed secretary, Thiru R. Mahesh Kumar, to honor our chief guest, Professor Sean Rigby. Sir, please. Thank you, sir. I would like to invite Thiru V.P.V. Periyasamy, our joint secretary. You start. Introduction of the theme. We must have a theme, a goal, a purpose in our lives. Likewise, he told me to stop with the already. Wait, you continue. We must have a theme, a goal, a purpose in our lives. Likewise, we have a wonderful theme today. I'm immensely pleased to welcome the person who has motivated many people by being a living example by sharing his expertise and knowledge, who is none other than Professor Anant Achari, Principal, to introduce the theme. Sir, please.
Good morning. Right. Energy is high, and that is what is the topic of the conference also. So I think the theme is introduced. Ganesh Murthy, thank you very much. You have done two work together. You have given a welcome to all, and along with that, you have made everybody to do yogasanas by clapping and keeping themselves awake for the whole day. Thank you. I take this opportunity to once again welcome all the dignitaries sitting on the dais and the professors, faculty members, heads of the department of the various departments of Kamraj College of Engineering and Technology, and the faculty members who have come to this college to participate in this international conference on sustainable development on energy and environment. And the young participants who may be from the various levels of education undergraduate and postgraduate, PhD, and today and for the next 2 more days, you are all here to learn and not to teach. You may be presenting your work, and through that work, you're going to learn. So be ready. Are you all ready, the participants? Those who are going to present a poster and oral presentation? Yeah? Yeah. Because people will ask you several questions, and that is what is learning. Right? Right. So it gives me an immense pleasure to introduce the theme of this international conference on sustainable development on energy and environment, and to this very inspiring gathering, a beautiful combination of mind that takes care of nature and future. If we take care of nature, it will take care of our future. The objective of this conference is to deliberate the current issues on energy and environment at a multidisciplinary level. It is not the single. Many of you might have come from biotechnology department, but energy and environment is everybody's issue, is everybody's work to protect the environment. To bring sustainable solution, the word sustainable is a very important. It is not an ordinary word. It is a sustainable solutions. We may have solution for many things, but today we solve the problem. Tomorrow it becomes a problem. The solution itself. So, to bring sustainable solutions for energy crisis and environmental remediation through simple, cost-effective measures that can be adopted in practical life. So it should not be cumbersome also. Like a very simple solution, they say, segregate all the waste based on their nature of degradability. Degradable, non-degradable, hazardous. Keep them separate, right? So that you can have a different kinds of plan. And once we talk about the energy and environment, that means it's a very wide area, and wider the area, wider is the scope. So, how to look at biological sources? And today, people are exploring algae towards this. Not much with the bacteria or the yeast. The algae as a source for energy and environment. How to effectively use the stored gases for energy purpose. Lot of hydrogen is available in atmosphere. How we are going to use that as a source of energy. Hydrogen gas is produced as a byproduct of anaerobic digestion, along with the hydrogen sulfide gas, carbon dioxide, methane, carbon monoxides, and lot of others, SOx and NOx gases. How do we separate that? Producing hydrogen is very easy, but bottling it is very difficult. That means the storage is very difficult. So how do we work on that? What is the latest update on biofuels and biorefineries, the concepts and the techniques and tools that is used? Again, you all need to be very careful with the word sustainable. The technology is sustainable only when it addresses the current problems, and also it possesses the solutions for the problems which will be encountered in future. And future, that does not mean that just 5 years or 10 years. It should be everlasting, maybe a time scale of 100 years. You should start thinking that the technological sustainability, the technology should sustain for 100 years. Of course, the technology is a very fluid. Every day it is changing. Every day new technologies are coming up, but can they be sustainable? That is the question, and that is what we will be looking at. How to effectively convert waste to wealth. Now, this topic has even gone to the primary schools. Art from waste, right? When you say art from waste, that art is not a waste, it is the art from the waste. So you are converting a meaningful product from the waste material. But one thing you should also keep in your mind, that when you regenerate certain thing from the waste, what happens to the residual waste? Because everything is not convertible. So there will be residual waste. Of course, you can talk that we have minimized the volume of the waste. Earlier it was 1 cubic meter. Now it is reduced to 1 liter. But today you are talking about 1 day's waste. Imagine of 365 days waste, that is 1 year. So if you convert that 1 cubic meter to 1 cubic centimeter into 365 days, into so many years you add. So this residual waste is also going to become another problem in future. So converting them into a meaningful product, converting for the energy production and environmental cleaning. Another theme area is current understandings and international scenario on water and air pollution. Water is the basis of life, and air is also the basis of life. And this is the great wealth on planet Earth. Without these two, you cannot live. Good quality water, good quality air, good quality of life. You should relate like this. Bad quality of water, bad quality of air, bad quality of life, because these suspended particles or the air contaminating with a gas would lead to variety of diseases. The bad quality of water would bring variety of infections to the body, and not only to human, it is to animal, and the same thing is going to the plants also. So we are the consumer. Animals and the human are the consumers. So we need to see it from a different perspective. Another theme is how we use different material for energy and environment management. First thing is a technology. Second one is the management. Science, engineering, and technology you put together. Second one, how are we going to manage the energy, manage the environment, manage the clean environment, manage a good quality of air, good quality of water, and good quality of living space. These broad areas, I think you will also hear the experts talking about this, and they will be giving you their own view through their research which they have done. And I'm confident that the topics and the theme area would certainly allow all of us to think differently and bring benefit for the current as well as the future generation. The idea is here to learn, relearn, but before that, you need to unlearn. You may be thinking that your presentations are the best one, but you should also be able to hear that others are also working. You will get some good idea from there, and then you can continue doing those idea in your research centers. So we have a great resource persons here of a national and international repute, and all the researchers, the students, It is a wonderful platform for all of you to interact, get to learn, and in a way, you can also exchange your novel idea. You can also think how your novel idea can be made workable while interacting with the dignitaries who have come here to deliver the plenary lectures and the guest speakers and also the Young Scientist Award. This will give you a lot of experience, and it will be good for the scientific organization, and also the conference will end in a meaningful way. Caring, sharing, and taking important decisions at appropriate time is the important key. Care for nature, share your views, and take an important decision on the correct time. And this we have seen through the organizing committee, the students as well as the faculty members, how they have worked for the extended hours and interacting, compiling the scientific reports and presentations. With this, I extend a warm and cordial welcome to scientists from the other countries, Young Scientist Awardee, and the scientists from our own nation, the researchers from this country, and the students from the different institutions, my dear students, colleagues, and finally, the office bearers, without whose support this day would not have been possible. Let's stay connected and create a better today and the best tomorrow. Thank you. Welcome you all once again.
Thank you, sir. I deem it a great privilege to invite the man of faithfulness and fidelity, our Secretary, Thiru R. Mahesh Kumar, to felicitate the gathering. Sir, please.
Good morning, everyone. It is my immense pleasure to greet our Biotech Technology Department and the coordinators. I extend my warm welcome to our chief guest from Nottingham University, Shan Rigby, and other resource persons, scientists, students from various institutions, and our heads of the department and faculties. Today, the conference topic is Sustainable Development, Energy and Environment. This is very nicely named because whenever we are producing the energy, it should not affect the environment. This is the main aim for this conference. So we have to balance it. So I have seen all the topics. It's all very, very interesting topics. Gas storage for energy applications. This topic to be delivered by Mr. Rigby, Director of Geoenergy Resource Center, Faculty of Engineering, University of Nottingham, UK. Next one is biofuels and biorefineries. And various topics, all are interesting. The materials for energy and environment system. So 3-day conference, students please involve yourselves And this is a very good opportunity to have a very good experience. As principal said, please interact with the resource person and get more knowledge and involvement. Being a secretary of this institution, I take this opportunity. I would like to request all the heads of the departments to conduct a international conference like this. This is a very starting point. So please work on it. I once again congratulate all the coordinators for organizing this function. And this is the right time to conduct this type of conference on this topic, because we are facing various problems, and now we are having very good awareness. This awareness has been developed in energy. In most of the factories, they are having the energy auditor now. They are appointing as a energy auditor. So very good awareness in all the industries field, and even in our homes also we are taking our steps to reduce how to economic wisely we can use this energy. Last month I went to Thailand. In all the rice millers, they are having their own what you call boilers. Boilers are producing stream in some frequency, but they are using the very reduced. What is the unit? I don't know, but they are having the reduction valve. Then they are using. They are all changing the reduction valve. Then I asked, why you are changing all the reduction valves? What is the necessity? They told they are bypassing the excess energy, and they are making a small turbine to make a power. That government has giving subsidy for the conversion of this energy. So this is the right time. Really, we are all expecting. We are eagerly expecting to witness our chief guest address. Thank you very much. All the best.
Thank you, sir. I would like to invite our esteemed secretary, Thiru R. Mahesh Kumar, to honor our chief guest, Professor Sean Rigby, with a memento. Sir, please. Thank you, sir. I would like to now invite our beloved Joint Secretary, Thiru V. Periyasamy, to honor our chief guest, Dr. N. Tajuddin. Sir, please. Thank you, sir. I would like to invite our treasurer, Thiru MSPRN Prashant Kumar, to honor our chief guest, Dr. R. Babu Rajendran. Thank you, sir. I would like to invite Dr. D. Padinattam Padiyan, Research Advisor of Kamraj College of Engineering and Technology, to honor our chief guest, Dr. V. Siva Subramanian.
Thank you, dignitaries. Now, I would like to invite the dignitaries to release the souvenir. Thank you, dignitaries. Teachers who love teaching teach students to love learning. I would like to invite our lovely teacher, Dr. Vasanthi, Professor, Head of the Department of Biotechnology, and Vice Principal of our college, to introduce the chief guest.
Good morning, one and all present here. It's one of the proudest moments of my life where I've had this opportunity to be part of the organizing team of the first of its kind in the institution, an international conference by the Department of Biotechnology on the theme Sustainable Development in Energy and Environment. Today, I am also blessed to be the leader of a team of young, sincere, dedicated, hardworking researchers that comprises of the principal, the senior professor of the department, the colleagues from the various streams of biotechnology, and my dear student participants and other heads of the departments of all the branches of engineering and technology of our institution who are committed in understanding issues that challenge the very existence of mankind in planet Earth. These kind of conferences are platforms where we need to admit our mistakes, what went wrong with respect to concepts, with respect to technologies, how we can reassure them, can we move ahead with innovative solutions, cost-effective solutions, at the same time be aware of not making any mistakes again. Of not making any mistakes again that would challenge more and more the researchers of the globe. Energy and environment are the best things that has happened to mankind. Be it biothermal energy or the power energy which drives engineering innovations and technology, anything and everything has to be purposeful, meaningful, efficient, storable, and consumable and renewable. So when are we going to focus on this? I thank the organizing secretaries, Professor Anant Achari, Dr. Ganesh Murthy, and Dr. Karthik Kumar for taking this need of the hour topic to be discussed and deliberated and to create awareness in the mind of young researchers. Work on concepts, work on tools, develop solutions, but please take care if they are sustainable. You have a long list of speakers, resource person across the globe. Professor Sean Rigby from University of Nottingham, a lot of scientists from our homeland, Professor Tajuddin, Dr. Shyam's guru and his research collaborator, Dr. Babu Rajendran, Dr. Sivasubramanian, Dr. Prakash Maran, the young scientists. The first time the Department of Biotechnology is also constituted Bharat Ratna Kamaraj Young Scientist Award, which also carries a citation and cash prize to encourage young researchers who are doing conscious environmental issue-related research. So this backdrop, I am also elated to inform the August gathering that the Department of Electrical Engineering of our college is getting ready with their international conference that would be organized on 4th and 5th of October this year on advanced technologies in electrical engineering. Why is that our management is particular and have been supporting us? Professor Padanatambadian, every time when he encourages us to apply for project proposals, he says, try to bring international researchers. You can act locally, but you need to know global things. You need to have a far-fetched global vision. I think the purpose of having international conferences is to understand what is the level of knowledge and technology in the better parts of the world. What is the problem with underdeveloped countries? Can all of us come together in a scientific gathering, discuss and take support from each other to develop sustainable solutions? This is the purpose of international conference. It is not a namesake international conference. And Dr. Kalyani, who is the head of the Department of Electrical Engineering, has got a grant from the Indian government support for conducting their international conferences. On behalf of the management, principal, the Department of Biotechnology, behalf of the institution, on behalf of the Department of Electrical Engineering, and the other departments of our institution, which will be organizing a series of international conference, my sincere appeal to the young researchers and student communities. We have brought galaxy of people working on different aspects of energy only to make you people interact. As principal rightly pointed out, be prepared to learn, unlearn, relearn. Start asking questions. Let it be even a simple, illogical question. Questioning is the beginning of knowledge, flourishing. So please make the best use of the opportunity. We could only provide the platform. It is the young researchers and the student participants who are going to add purpose and meaning to this international conference. Connect with them, interact with them, talk with them. And I'm elated now to introduce the plenary lecturer and the chief guest of today's inaugural function, the other guest of honors. I present unto you the profile of our international researcher, guest of honor, Professor Sean Rigby from the University of Nottingham, UK. He completed his Master's in Engineering and PhD degree in Chemical Engineering at the University of Cambridge, UK. His PhD research was completed under the supervision of his guide, Professor Lynn Gladden. After his doctoral program, he worked for the catalysis business of ICI, a reputed international organization known as Catalico, for 4 years as a process engineer and research manager for the company range of HCl and organochloride absorbents. In 2000, he left ICI, the company, and became an academician at the University of Bath, UK. In 2010, Professor Shan moved to the Department of Chemical and Environmental Engineering at the University of Nottingham, UK, where he is currently the Professor of Chemical Engineering Department. He is also the founder of the Geoenergy Research Center, which was founded by him in the year 2015 in his institution. His research interests includes catalysis, NMR and MRI, the most powerful tools of 21st century, because the instrument per se is complicated, the technique per se is complicated, and more complicated is the interpretation of the data that come out of an NMR, the spectrums, and the MRIs. Carbon sequestration is also his area of interest. He also works on fuel cells, clean fossil fuel technology. I am deeply attracted by this term, clean fossil fuel technology, and I'm eagerly waiting to learn more from him in this dimension. He is also interested in controlled drug delivery systems. Professor Shan, to his credit, has completed funded projects worth nearly £3 million. He has published over 100 revered journals, papers, and he is also a fellow of the ICSDEE, and more interestingly, he is the fellow of IUPAC. All our students are familiar with the terminology IUPAC and its relevance and significance. He is also the fellow of the Geological Society of London. Thank you so much, Professor Shan, Rigby, for taking time amidst your busy schedule and for coming all the way from UK to meet researchers of our homeland and young, dynamic minds of this country. We feel very proud to have you with us, and we deem it a great privilege to invite you to share your research experience, the cultural spectrum of the country to which you belong, the opportunities that exist for young scientists to collaborate with institutions of yours and other institutions in your country. Let this international conference be a beginning of great future. And I promise our principal that we would work on his philosophy for a better today and the best tomorrow as young researchers. Thank you one and all. Have a pleasant stay at Kamaraj College of Engineering and Technology. It's been a long journey working for this conference. There could be small shortcomings. Kindly forgive us and please bring it to our knowledge and give us an opportunity to keep improving, because our management and our head of the institution have given us the philosophy of keep improving continuously. God bless each one of you. Thank you. Now, with all your enthusiastic reception, I request Professor Shan Rigby to take his honor of the day.
Yeah, the point is swift. Yeah, it's fine.
Audience, please maintain silence.
Okay. All right. Thank you very much. I'd just like to extend my thanks to the organising committee and the management of the college for inviting me and for your hospitality. It's been wonderful. Thank you. I thought I'd just start, just for those people who don't know, where Nottingham is in the UK. So this is just a quick little map of the UK, and Nottingham is right in the middle of England. It's quite famous for, as I explained yesterday, Robin Hood. If you've heard of Robin Hood, the sheriff of Nottingham was the baddie in the Robin Hood stories, if you see the films. This is an aerial shot of our campus. So we have our lake, and the main building here was built in the 1920s. And then there's a parkland in the middle, and then the science faculties are all down here. And then we have all our halls and the arts faculties at this end of the campus. So it's a big green park. So that's where I'm from. Also, as we mentioned, I head the Geoenergy Research Centre. So this is our research centre for anything to do with energy and the Earth. So geothermal energy, carbon sequestration, oil and gas we've done in the past. And we have basically, it's a collaboration between all the departments of our university, and on the outskirts of Nottingham is the British government's geological survey in a place called Keyworth in Nottingham. So we work very closely with geologists. And we have 5 staff who are from all over the world. They're from Belgium, from Indonesia, from Italy. And we work together with our Government Research Council and the EU and various different companies. So just to give you some idea of what we do. So we're interested in anything to do with geoenergy, and we work on a range of different length scales. So not just, if you talk about the Earth and the environment, you tend to think of very big length scales, big scale processes. We work also down to very small scales. So we're very interested in anything to do with the Earth and energy, and how it affects the environment. So we particularly look at flow and multi-scale modeling of flow in porous materials like rocks, and also the chemistry that goes on the Earth. So anything where energy processes are going to affect the rocks and how they change. So we want to make sure that this is important for looking at the impact of our energy extraction or development processes on the environment. So just some examples. So we do large-scale geological work, so mapping reservoirs or rock types across the world. So this is just very typical geology. So we're taking geological maps in Spain of the distribution of different sorts of rocks in Spain. But more relevant to here is we're looking at gas storage, basically for fuel. So ways in which you might store fuel gases, like hydrogen. So in England, there are already developments of infrastructure for hydrogen in urban areas in certain parts of England where they have capacity for storage. And it tends to be where they used to mine salt. So the northwest of England, we have salt mines that are used now for hydrogen storage. The trouble is that if you store hydrogen underground, it can get contaminated, and it causes problems for using it as a fuel. So we're looking at what happens there in the storage. And the other thing is, if we're going to transition to new fuels, you may have to still use fossil fuels. So what we're looking at also is a big research area is carbon storage. So how you sequester CO2 underground, what it does. And this is a really, really big research area because one of our sort of flagship things is we have our own carbon storage site in Nottingham. So we're actually doing trials of injection of CO2 into the rock structure underneath Nottingham to test what will happen to it. Will it stay there? What happens when it leaks? A big concern for people if you want to store CO2 is whether it will leak. There are lots of stories, unfortunate incidents from volcanoes where released CO2 and it's gone down valleys and pooled in the bottom of a valley and then killed animals from CO2. So lots of people are worried about what will happen if you store CO2 near their homes. And in the UK, it's a very small island. So if we store CO2 onshore, it's going to be very close to people. So they're very interested in knowing what happens if it's released. So we're doing tests of injection. So these are wells. So these are wells we drilled to test, to drill into the rocks. So we have sandstone rocks that are very, very similar to the natural gas fields in the south of the North Sea. And UK are planning to use those potentially for storing CO2. So the old hydrocarbon reservoirs that produced oil or gas, you can use to put back CO2 or use to store fuel gases like hydrogen. So what we want to know is, will these things leak? This is the problem. So our test bed, we're doing lots and lots of studies of testing for leakage. So we do lots of programs of once you inject the CO2, you see if it rises to the surface and if you can detect it. So we're working on sensors for detecting CO2 coming out of the ground and monitoring CO2 release from the air, from things like drones, and mapping the release. So you create sort of maps to detect if it's leaking. You can also look at on the ground. You're interested in what happens to groundwater. So obviously you don't want to contaminate drinking water aquifers nearby. And so what we're doing is looking at lots of different length scales from the size of the reservoir itself down to the pores in the rock where we store the CO2. So this involves a big interdisciplinary effort, as been said. So my research centre includes chemical engineers like myself. We have chemists, we have physicists, we have mathematicians, we have geologists. And we're all working together to develop new ways of getting sustainable energy. And importantly at the moment is the transition from the old oil and gas to new fossil fuels. Sorry, new sustainable fuels. So we're looking at that transition without disrupting the world economy and still supplying the energy demand. So the energy is still demand is still going up. So we need to know how we can do that. And our site, the GTB, is used basically for testing carbon sequestration and making sure that it's potentially a way that we can move from oil and gas to sustainable fuels. So what I'm going to talk about today is one example of some of the work we're doing and also the sort of techniques that we develop. So a lot of the work I do myself as a chemical engineer is on technique development. If there's one thing that sort of unifies all my research, it's holes. I look at things with holes. So all the research areas that were mentioned that I look at all have one thing in common. They have lots of holes in. So I work on understanding how gases and liquids move around inside things with holes in. And in particular, one application that's relevant for future energy is where we're going to store gas. So if we're going to store hydrogen to use as a new fuel for the future, where can we put it? And there's lots of ideas about where that might be, but whether it's safe, because obviously hydrogen is very dangerous, it's explosive. Infrastructure that involves storage, you need to be sure that it's going to stay put. So this is a diagram that was put out by the European Union to suggestions for future energy infrastructure. So there's obviously windmills, solar power, maybe to generate electricity, maybe to store in batteries, but that's quite expensive. And maybe store in some other way. So maybe you to split water to make hydrogen. They also talk about, so there's lots of like hydrogen generation and hydrogen fuel stations. But the big thing missing from this diagram is where are we going to store the gas? So if you're going to make lots of gas, where are you going to store it? So one of the suggestions is, like I said, the old salt mines. But the other place you can put it is old reservoir rocks. So you can send the gas down into reservoir rocks. And a key issue for that is the cat rock, the seal. So if you're going to use underground storage for gases, be it CO2 or hydrogen, you need to have a proper seal. Otherwise, we'll leak. And the issue has been that these previous reservoir rocks, the seal's been broken to extract oil and gas potentially, or mine salt. So you've disrupted that cat rock, and you maybe done all sorts of processes to it that may have disrupted it. So what we want to look at is how the integrity of seals. So what we're going to do, the reason we need to look at shales is because they're typically the seal cat rock for most reservoirs. So as I've been saying, hydrogen's a potential alternative fuel source, and it can be stored underground, and the seal rock for that would be shale. But it's not possible in geological storage sites to test every single inch of the cat rock to check whether it's sealed. So what we need to do is understand what happens to the rock when we recover hydrocarbons or recover gas, or we do something to it, or what happens to it naturally in the environment to see whether it's going to make a proper seal. Also, you can use these reservoirs for all sorts of other potential renewable energy sources. So one idea is to compress air and send it into the reservoir. So you can temporarily store energy as compressed air underground in the reservoir. But again, you need to make sure that the reservoir seal is secure. The biggest problem we've had is that in the past, the reservoirs that we might look for to store gas have undergone lots of different geological processes that involve heat treatment of the rock that can basically disrupt it and destroy the structure and create holes. And so, for instance, volcanic activity releases steam that will cause degeneration of the shale rock. Any sort of intervention in the reservoir by reservoir engineers who maybe extracted oil and gas, maybe use steam, would disrupt the rock. And what we're interested to know is what happens to the rock during these treatments, either natural or man-made by reservoir interventions, to see what happens to the rock, to know whether it will be good as a seal for gas storage. So what have we done? So the first thing we do is obtain some good examples of shale rocks, and we treat them to mimic what happens to those rocks, either by environmental processes or during reservoir engineering interventions that were used to extract hydrocarbons. And then we characterize them. And this is where my main research area is developing techniques. So what I'm going to talk about is some of the techniques we use for characterizing these porous rock materials. But they can be used for all sorts of other different porous materials. So catalysts, so if you're developing catalysts, particularly say for biofuels, they have a tendency to coke, and the structure changes, and it's very difficult for reactant molecules to get into the catalyst and react because of the deposition of coke that forms. And so you're interested in the changes that happen during that chemical reaction. If you're doing chromatography or separations in biotechnology, again, you get build-up of debris in the chromatography column, structural changes that are important that affect the performance. And what I'm interested in is the interaction between the structure we get from these techniques, and mass transport. So how the changes you have in the pore structure in a rock or a catalyst or a column affect its performance in terms of mass transport. So what I'm going to talk about is some of my techniques we've developed for doing that. And hopefully they're all not just of interest in gas storage, but maybe to the systems that you look at. So just to talk about the shales that we got, they come from England. So they're basically underneath Nottingham is a big shale deposit that is potentially could use for extracting gas, but also potentially subsequently for storage. So we take the shale, core the shale from deep underground, from about 600, 700 meters down, and then take it to the lab. And this is what it looks like, okay? So what we have here is an X-ray CT image of a chip of the shale rock. And then over here we have an electron microscopy picture. So it's basically a much closer, I don't know if you can see the scale bar. Yeah, so this is about 1,000 microns, so a millimeter. So this is several millimeters across. And then this is microns, okay? And if we look at the large-scale structure of the rock, the bright areas correspond to things like iron pyrites. The dark areas are carbon. So if you look under the microscope, what we see, these black areas here are carbon. Those basically from organic matter that was in the rock when it formed. And that is where you get things like shale gas and shale oil from. Okay, so this stuff can be in different sorts of forms that eventually may make oil. So different shales have different amounts of carbon in. The cap rocks have very little carbon. The reservoir rocks have a lot. And this is the stuff that you want to get out during shale gas extraction. So this is where the space comes for when we want to store gas afterwards. So the treatment we gave it is to represent what happens to the rock either geologically. So during, once a mudstone has been laid down at the bottom of a river, after time it gets buried and compressed, and it might go up and down in the earth, being heated and cooled, subjected to high pressure and temperature that change the rock. And what we're interested to know is what to mimic that in the lab to see what happens to the rock, so we know what the rock is going to be like underground, and we'll know whether there's going to be any holes in it. Or also, if the rock has been a reservoir rock and been treated to various different sort of hydrothermal treatments from steam, what that effect has on the rock. Because what that's going to do is influence how the integrity of the seal of the shale and how much pore space we're going to have for storing gas if it's a reservoir. So one of the main techniques using, if you're looking at systems for gas, is nitrogen absorption. So just a brief introduction for those people who might not know anything about it. The basic experiment, we take a porous material, we dry it out, we evacuate air and water vapor that's been from the atmosphere, and then we apply a steadily increasing pressure of pure nitrogen up to the saturated vapor pressure. And we do this at 77 Kelvin, the boiling point of nitrogen, and you measure the amount of gas that absorbs a particular pressure. So this is also the key experiment for gas storage. So measuring how much gas will be stored at given pressure. So as you increase the pressure, the gas starts to form a layer on the surface, like a carpet of gas. So this is what we call the BET region. So if you've ever had to measure the surface area of something using the BET equation, this is the bit of the isotherm you use. And then later, the gas actually condenses out as a liquid inside the pores in a process called capillary condensation. And you get this big step up in amount of gas. And this is governed by what's called the Kelvin equation. So the pressure you get P is inversely related to the pore size. Okay, the log of the pressure is inversely related to the pore size. So anyway, as we go higher and higher in pressure, you condense out gas in bigger and bigger pores. So the higher the pressure, the more gas there will be condensed out as condensate, liquid-like phase in the pores. So this method is used to evaluate the pore structure. So what we do is, I mentioned that the shale is a bit like, it contains carbon and it contains clay. So it contains organic phase and it contains inorganic phase. And so it's a bit like a chessboard with two different sites. So you have white squares on a chessboard and black squares on a chessboard. So you can imagine the black squares are like the carbon and the white squares are the inorganic phase. And the gas absorbs differently in the two different phases. So we measure the gas absorbing on those two different phases. And we get measures of the surface area. So, So the important thing are these numbers down here. So the surface area starts out at about 60 meters squared per gram and rises to about 130 meters squared per gram. If you want to know what that sort of area corresponds to, it's a bit like having a soccer pitch buried away inside a piece of blackboard chalk or a tablet. So you have enormous area buried away inside tiny little volume. And that's why you can store a lot of gas in a very small space. It's because you have an enormous surface area in a very, very tiny amount of mass. So like I say, it's a soccer pitch, a football pitch, buried away in the size of something, the end of my fingernail, or the cap of this bottle. Very tiny space. So this is why the gas absorption is very important, to find the surface area. That gives you the capacity for the storage of gas. And it also, if you happen to be interested in extracting gases, then how much gas is likely to be there. So it's very important to get this number correct. So what we have to do is work on a lot of different modeling methods to understand how gas absorbs on the surface to get an accurate value of this number. So if you just use the traditional BET method, you find it's 18 meters squared per gram, but using more complicated model, we get 3 times that. So this can make a very big difference to evaluating how much gas is going to be stored in the rock. If you don't get this number right, you can't evaluate the gas storage capacity properly. So we work on ways of getting this more accurate. If we move to the other end of the isotherm, we get this condensation. The other area where people underestimate the storage capacity is that the standard machines that you can buy to do gas absorption experiments, like micromeritics or quantachrome, they were designed to stop before you reach the saturation point of the gas. So they seriously underestimate the amount of gas that condenses in the pores to form liquid. So what we have here, as an example, is an isotherm for a shale rock. And the black symbols there represent the standard conventional experiment people do. And so if you read a lot of the literature, that's what they'll see. So this is a very classic isotherm for shale. But if we fool the instrument into filling up the pore space completely and utterly with nitrogen, and then come back down, we get, this black line here, okay? So the big thing to take home is this big gap just here. So all the experiments that people do to measure absorption capacity seriously underestimate the gas storage capacity because they miss this bit here, okay? So this is almost a third to a half of the space is missing, okay? So the gas experiment won't evaluate proper storage capacity. So what I'm just going to talk about is how you get the gas out of the ground. So for the gas to evaporate, it has to be, the liquid to evaporate, it has to be next door to a vapor pocket. And the liquid to evaporate, there has to be a free meniscus. If the liquid is trapped here, behind this small neck, it can't evaporate. So the tiny little holes like this block the vapor to escape. So if you want your gas to come out of the pores, you have to drop the pressure a long way to evaporate this gas here, this liquid here, into the gas phase before you can get all the other liquid. So what can happen is if you have very, very narrow necks inside the shale rocks, they block the movement of the gas out. So what we do is use fancy nitrogen experiments to look at the structure of the rock and find out if we have these narrow necks. So we can do these experiments to find out whether these necks exist. But what people try and do to try and see the bigger pores in the rock that I've been talking about that were missed is another method. It's called Mercury Porosimetry. So this is a very standard method in the oil industry for looking at rocks, and in the catalyst industry for looking at catalyst pellets. And what you do is evacuate the sample and then immerse it in mercury and then intrude the mercury under pressure. So mercury is a non-wetting liquid, so it won't enter pores unless you raise the pressure. And the smaller the pore, the higher the pressure you need. So the relationship is inversely with the pressure. So you raise the pressure of mercury outside your sample, and it will go into smaller and smaller pores. Now, as you can understand, just the mere mention of the word mercury, this isn't very sustainable. Lots of people have doubts about using mercury. So what we try and do is use now this condensation process that can study these big pores. So what people use is mercury porosimetry to study these big pores. But what we do is a very special experiment where what you want to know, what you've got to imagine is your rock is like a road network. So imagine you've got the highways, the motorways, and then you have smaller roads where the gas goes to be stored. And what we want to know is how important are the different sorts of pores in the rock to mass transport. So you want to know what are the key roads. So in England, we have big motorways like the M1 that have lots and lots of traffic, and if they ever shut down due to roadworks, they bring all the traffic to a halt, okay? Or the M25 motorway around London, that was ever brought to a halt with roadworks, all the traffic would seize up. So what you're interested in porous materials is knowing the effect of shutting down different pores or creating different pores. So if you've got make pores, how much do they contribute to mass transport? So the way we study that is basically to put the roadworks into the roads. So we shut down the pores by filling them with mercury. So this is just a schematic to explain the experiment. So if you have an empty pore space, you can absorb the gas everywhere. But what we do is then do mercury porosimetry and fill the pore space with mercury, and it tends to get stuck in the big pores. So it's like shutting down the motorways. You shut off the biggest roads you have in your country and see what happens to the traffic. It's all forced to go down the little lanes. So what we do is then study how the gas goes into those lanes. So this is just some examples of experimental data. So this is what a mercury porosimetry experiment data looks like. You start with big pores, low pressure, to small pores, a high pressure. You intrude the mercury goes in, and when it finally reaches the pressure you need to intrude the pores on the surface of the rock, all the mercury will go in. And then when you reach the highest pressure, you can go to it stops, and then you release the pressure, and the mercury gets stuck. So this is the mercury getting stuck. So it goes in this way and comes out that way, and it's entrapped. And this is the roadworks. This is what we use to block the pores. So we can look at shale. So what we're looking at here, the solid line is the initial shale, and then it's been treated with steam, as I mentioned. So it's been a simulated natural process of treatment with steam, or an intervention in a reservoir to release gas. And you can see that the amount of space in the rock expands. So you go from untreated here to treated in the dashed line up there. So you get a massive increase in holes. So if this was a shale that you'd produce gas from and you wanted to store gas, you've just increased the capacity enormously. And what we want to know is, what's the nature of that new porosity? What is it like? What sort of pores do we have? And what we can do is block them with the mercury and then do an experiment afterwards. So these solid symbols represent the experiment of gas absorption after we've entrapped the mercury. So we can see that the mercury gives rise to now an isotherm that looks just like it did before we started. So what that's telling us is that the pores we introduced are completely brand new. It's a completely new network that didn't exist in the rock before, because we're getting back to almost what we started with when we block off the new structure with mercury. So that means we need to start looking in the rock where and we can look at what effect that has on the movement of gas. So we can watch how the gas moves when it goes into the rock before we treat it, and after we treat it when it's empty, and then we can fill up those new pores with mercury. So it's like putting roadworks on your highway, and then follow the gas afterwards. And what you find, just to draw attention, is there's a factor of 1,000 difference in the gas rate, flow of gas, between before and after filling the new pores with mercury. So what we've done is increase by the treatment of the rock the rate of gas flow by a factor of 1,000. What that will mean is that if that's a gas storage reservoir, we've improved the ability of gas to go in and out. It's also very critical for estimating gas for shale gas, because if the rock underground has experienced natural steaming, it will release the gas, and basically all the gas that you will go looking for has escaped. So this makes a big difference to estimates of reserves of gas, and also what that means in terms of how easy it is to store the gas. So what this is saying is this shale, we've improved the ability of the gas to go in and out by a whole factor of 1,000, which is big, big news in terms of storage. So what these techniques are showing us is you could seriously underestimate gas storage capacity if you use standard methods, and the heat treatment has improved the mass transport enormously. So if you go back and look at the rock, so we take some X-ray pictures of the rock. So these are like X-ray pictures you'd have if you go to the hospital, and we look at what happens to the rock before and afterwards. So this is before, so it's a bit featureless. There's not a lot here. You see some of the carbon and maybe one or two cracks, okay? But it's mostly featureless. It's mostly clay, and the bright white specks are often iron pyrites. But then we've cooked this shale in steam to simulate either natural igneous processes or reservoir interventions, and you get a big difference. So what happens is all these big spaces now open out. So we've gone from having a system with very, very tiny pores, like lots of country lanes, very narrow roads, tracks, where there's very little room for the gas to move around, to having these big motorways, big highways now for the gas. So the treatment opens up these big regions. And what we're interested in knowing is, where's that happened? So we then fill the pore structure with mercury and image it. So this is the image of a chip of rock. So this is what the rock looks like here. And the little red dots in there are the mercury trapped inside those big pores that we've made. So the mercury is acting like a tracer for the motorways in the rock. So this is all the storage capacity we've generated. So this is all those spaces filled up with mercury. And this is a slice through this structure. So it's like a slice through, and you can see the red is where the mercury has gone. And we just take the pores themselves. And again, this is a slice through this structure. And what we've done is you can see the enormous amount of space that the extraction process, the treatment process generates. And you can potentially, for gas to come out of, and then for gas to go back in. So what this lets us do is see what we're doing to the rock and where the mercury is, and understand the changes we see in the rock structure and where they're forming. So we can look a lot closer. So we can go back to our micrograph before treatment. And as I mentioned, these black regions, you can do elemental analysis, and they're basically organic, carbon. So the red here corresponds to these black shapes in the electron micrograph, and they are basically the carbon, the kerogen, that would form oil or gas, okay? And then we treat that and see what changes we get. So if you look at the carbon here now, this is a rock that's been treated. So what hopefully you can see it's a bit blurry, but the carbon here, still a black shape, but it's got lots and lots of little bubbles in. I don't know if you can see them. But basically, it's a bit fuzzy, but basically what happens is the carbon starts to look like an Aero chocolate bar, if you've seen one. One of these chocolate bars with bubbles. Because all basically the volatiles in the carbon have evaporated. And also the rock crystals have all been annealed. So it all looks very rough. So if you look back at this image, all looks very crisp. All the edges of the rock, of the mineral grains are all very crisp and sharp and just fine. Whereas afterwards, they're all very much more roughened, and you can see all the holes that we've generated. So this structure here is where gas would maybe come out if it's a shale gas reservoir, or you could put gas CO2 in to store. And we can look and see what all those pores I was talking about, where they came from. And what it looks like is the destruction of some of the rocks. So there are carbonates in here that will decompose on treatment of heat. So the rock crystals will, like I say, anneal and leave these spaces, and we get bubbles in the carbon. So what's the conclusion? So what the main conclusions I'll say is that basically the conventional techniques that most people use to evaluate gas storage capacity in rocks seriously underestimate the amount of space there is for gas storage. Basically, the conventional methods miss lots and lots of pore volume for gas storage. These new methods we're showing help you understand how much storage space you've got and understand how easy it's going to be for gas to move in and out of these rocks, which is very important because obviously if you get demand increasing for energy, you need to get your gas out quickly. And we've shown that this treatment of the rock that this rock's undergone increases the rate at which the gas can leave or enter by a factor of 1,000. So the implications are that you need to understand the previous geological history of your gas storage reservoir and understand the effect that's likely to have on the rocks, either the reservoir rocks where you're going to store the gas or the seal rock. If the shale is going to be the seal rock. If you're going to use old oil and gas reservoirs to store gas, you need to understand what effect the reservoir engineering interventions had. So people have used enhanced oil recovery methods to get the hydrocarbons out of the ground. You need to understand what effect they've had on the rock, because it may destroy the cap rock, the seal, and stop it being useful for gas storage, or it may increase the capacity of the rock for storage. So we need to look at what happens to the rock and understand it so we can understand the viability of our reservoir for future storage of new fuels like hydrogen. So I'd just like to thank all the people that I work with in Nottingham with this sort of work and the funding we get from our Natural Environmental Research Council. And just to say, this is all the research areas that we work in. This one is the big one at the moment in England, is geothermal energy, but we work in all these sorts of areas. And all those techniques I've talked about come in useful too for all this sort of thing. Okay, thank you very much for listening.
Thank you, sir. The session is open for questions now.
I have a question to you. First of all, thank you so much for to a very interesting and a new area on gas utilization and its storable issues. My question is like, at the environmental level, there are a lot of activities that are taking place and the micro environment changes. So what is going to be the impact of the micro level environmental changes at this depth?
Which changes? Sorry.
The micro level environmental changes.
Okay, so the rock changes.
Yes.
I mean, the biggest issue is going to be for leakage. So for shallow, all this sort of thing, the CO2, well, I didn't talk about, the CO2 itself is acidic, as I mentioned yesterday. CO2 is an acidic gas, so it will react with the minerals underground, and if you're sealing it with cement, it reacts with the cement. So one of the big issues we look at also using these methods is the poor structural changes in the cement for the wells where you put the CO2. Because the tiny changes that happen at the pore scale, basically in terms of the reaction between the CO2 and the cement, for instance, influences how the integrity of the cement seal and how easy it's going to be for the gas to escape. So interested in that. The also issue is if you're going to use gas storage, the reservoirs for gas storage, the gas, like hydrogen, will react with the rock, so potentially reacts with the rock and contaminates the gas with all sorts of things. So you dissolve the minerals, react with the minerals, there's water down there, so you've got plenty of opportunity for chemical reaction. And so what you're interested in knowing is how the gas interacts with the rock. So we call it fluid rock interactions. And because that will affect, you might release sulfur from the minerals into the gas. And therefore, so we work on that as well. So there's a lot of work, like I said, the Geoenergy Research Centre, we have a geochemist, and we do a lot of work on assessing the interactions between stored gas and the rock to see what contaminants are likely to enter the rock in different sorts of rock reservoirs. So what are the dangers of contamination? Because you don't want to you have very clean hydrogen, you make very clean hydrogen, you don't want to contaminate it with sulfur or something from the rocks.
Good morning. Wonderful work you have done, but I have few clarifications from your work. You have taken nitrogen as a model gas.
Yes.
For the mass transfer studies.
Yes.
Do you feel that the mass transfer model and the diffusion of gases will vary as per the molecular weight of the gas and or atomic radius of the gas?
Yeah, yes. Obviously, nitrogen is very much bigger than hydrogen. So nitrogen can't get into the very smallest pores. I mean, what I haven't talked about is we do look at do the same experiments with other gases. So we do it with CO2, we could do rate of uptake of gas, different hydrogen, methane, CO2, lots of other different gases, just to see the effect, what the accessibility of the pore structure is for different gases. So hydrogen being very small can get in even smaller pores.
Mostly the nitrogen is non-reactive.
Yeah, that's the main reason.
Yeah, but if you take two rocks for the storage of hydrogen, as you said, it may react. Certainly it could react and form another hydrocarbon kind of substances.
Yes.
So how the method or the technology can be used for the storage of hydrogen?
So for hydrogen?
For the storage of hydrogen gas.
Yeah, so the biggest issue in England is finding reservoirs at all. So at the moment, like I mentioned, hydrogen storage only takes place in old salt mines, in what we call salt domes. So what we need is to look for new types of reservoir. So what the work is all about is trying to understand the geology of new types of reservoir to see how useful they're going to be for storage of hydrogen. Hydrogen is very small gas, so it will find any crack, any hole to escape. So what we want to evaluate is how well the reservoir is going to hold onto the hydrogen and it's not going to leak to the surface. So it's very important to understand the holes, the rock structure, to see how much hydrogen will be staying there for how long.
Another question is, to increase the gas holding capacity, you have given a mercury treatment. You have treated the shell with the mercury to increase the holding of nitrogen gas. how safe mercury treatment will be to the nature.
All right, sorry, no, we're not going to use mercury in the environment. The mercury is just a way of assessing the size of the pores we have in the lab. In the environment, it will be steam. So the treatment you use on the rocks in the environment tends to be steam. So they inject steam to help recovery of oil, for instance, or CO2 for help recovery of oil. So a lot of the reservoir rocks have been treated with steam at high temperature, or CO2. And the CO2 is a chemical reagent, reacts with the rock. The steam, the water reacts with the rock, and also gives a little heat. So what we're interested in is what effect does that heat and chemical reaction have on the rock structure? How does it affect the integrity of seals for cat rocks? And how does it affect the capacity for storage? So what you find is these processes are very, very intense, and they generate a lot of changes in the rock. And so you potentially increase the capacity for storage from what you had before. So shale, after extraction, has got a lot more capacity for storage. So in America, they're looking at using old shale gas reservoirs for CO2 storage.
But here your work is based
Here?
all on the shell.
Yeah, so we use other rocks as well. So
Yeah,
looking at
but if you take another kind of rocks, what kind of treatment do you suggest
Oh, right.
to
So,
hold the gas?
So I mean, even if say you're doing CO2 storage, the CO2 is usually injected at supercritical conditions, and it's very corrosive. So there's a lot of changes in the rock when you add in the CO2. So when you pump down CO2, it actually, the rate of injection of CO2 can increase because the rock structure erodes and potentially gets bigger. However, you can also create fines, small grains of rock that will block the pores and shut down the porosity. So what we're interested in knowing is when you send gas into the rock, be it CO2 for storage, for sequestration, or hydrogen, what changes do we get? What sorts of changes do we have? And this work is all about understanding different sorts of changes. So changes to the number of pores, how big they are, how interconnected they are, and also changes to the chemistry. So we saw you lose the carbon. So the heat treatment drives away the carbon and leaves the void spaces where all those carbon pieces were. And that gives you capacity, okay, and improves the mass transport.
Your studies has clearly proved that it can absorb nitrogen. Okay. When you come to the case of hydrogen, its molecular weight is very low. Is there any study on shales to store hydrogen?
Is there any
study has been made on to store hydrogen in shale rocks?
In shale rocks?
Yeah.
Not that I know of yet.
I don't know.
It's mostly for the seals that we're interested in.
Okay.
So how for the seals for the moment. In England, most of it's, like I said, in old salt mines. So in northwest of England, in Cheshire, there's lots and lots of old salt mines where they injected hot water to dissolve the salt and dissolve it out. So there are large caverns that used to contain salt and now have just a layer of salt as a seal around the inside surface of the cavern. And they're used for tests of hydrogen storage for supplying infrastructure. But the problem we only have those in certain places in England. So there's only certain places. So if we want to have hydrogen fuel storage elsewhere in England, we've got to look at other sorts of reservoirs. So we have old mines, we have old gas reservoirs in the East Anglia and off the coast in the North Sea, sandstone reservoirs. And then, so what we're trying to, and in Scotland, they have more mudstone reservoirs, but all of them have shales and mudstones as the seal. So it's important for all of them.
Yeah. Palladium is well known to store hydrogen. How the shale will be better than palladium?
Shale will be better.
Palladium is well known to store hydrogen.
Oh, I see.
Yeah.
No, we're talking vast amounts of hydrogen.
How to compare it?
And it's basically, if you're going to use hydrogen as fuel to heat your home, power your home, you need vast amounts. So we have to store it in gas phase, compressed gas phase, and in a safe place. So on the surface, It's dangerous. So obviously, so what we're trying to do is store it underground, where it's
Underground.
safer. And you can store really, really big volumes.
Thank you. Thanks.
I have one question, but not to chief guest, but to our Dr. Ganesh Murthy. He has clearly explained the interested potential collaborations. Could you please explain how we are going to associate in future? What are the areas we can, feasible areas we can concentrate?
Currently, we are working in fuel cells and environment, microwave chemical processing. We are working on for the removal of biomass, lignin degradation using a microwave process. So also, professor is interested to student exchange program as well staff faculty exchange program for the PhD or postdoc in UK, University of Nottingham. Yesterday, I briefed about all the things, what are the scholarships are available in their universities and how, when they call, he explained well, professor explained well. So that in future we will get in touch. Of course, he has supported our conference paper that has to be published in a fuel journal, which is 5.128 impact factor. So we another 1 year we continuously keep in touch with Professor Sean Rigby for the post conference work. So meanwhile, I will see that where our student and other faculty and other dignitaries can be placed in appropriate way in University of Nottingham. Thank you very much for the opportunities. Thank you.
And also, I'd add, yesterday I was given a tour of your laboratories and met a lot of your colleagues. And I've heard a lot of interesting research work that sounds useful. I want to discuss further for potential collaborations. And there's a lot of things I can take home to discuss with my colleagues who work in biotechnology. As well, I can mention what the research work that's going on here and maybe get them in contact as well. So we have one of our big research themes in Nottingham is biotechnology and sustainable chemistry. And so we have a Professor Alex Conradi, who's Professor of Biotechnology. So I can go back and report to him what the sort of work going on here and see and encourage him to get in touch. And also, I'm interested in collaborating with a lot of the work that's going on here, particularly in nanoparticles. It sounds very interesting.
Yes. Also, Professor Rigby is working in nanotechnology field. And some of our colleagues are interested in nanotechnology field. So they are also will get in touch with Professor Sean Rigby. Thank you. And one more thing I would like to share. This has all happened because of Dr. Shiva Subramaniam, NIT Calcutta. We all met during SAR has conducted one conference, the same near energy and environment global challenges in the year of 2018. So where we discussed and met Professor Sean Rigby, and it was a long process to bring him here. Thank you. Thank you. Thank you, sir.
Very good afternoon to one and all, and thank you, sir, for sharing your work, whatever you have carried out in your university. I have one simple question. Actually, in your area of expertise, it was mentioned electromagnetic heavy oil recovery. So what type of work you have carried out so that we could see that whether we could also extend the scope of that work, whatever you have carried out related to oil recovery through electromagnetic fields?
Yeah, so one of the things we say in Nottingham is that we're working on developing new sustainable technology, but to fund that and to supply the energy we need, in the meantime, is we have to still continue to explore other resources like heavy oil. And obviously we're doing things like seized carbon capture and storage to mitigate that. But so one of the ways we work on is to use microwave technology to extract heavy oil. So it's very, very sticky. It's like treacle. And so it's very difficult to mobilize. And so what we do is use microwave heating to help mobilize the oil. So what we've found is that heavy oil will actually absorb microwave energy. So the resins and asphaltenes in heavy oil will absorb microwaves. So you can actually directly heat the oil. We thought we'd have to use some other method, but we've proven you can actually heat the heavy oil. And we're using it as part of a combined combustion and microwave heavy oil extraction process, where we actually upgrade oil underground. So the other big use for microwaves is to actually carry out catalysis and oil upgrading reactions underground. So you don't have to build a plant on the surface. You can do all the upgrading underground using catalysts and microwaves. So we're interested in effectively putting chemical plants underground so it doesn't affect the environment on the surface.
Thank you, sir. And one more thing to answer to the question what Secretary Sir was talking. In our department, in the Department of Electrical and Electronics Engineering, our PG students and researchers, they are working on proton electron membrane fuel cells. They are extensively working on that. So we would feel very happy to join hands with your university in submitting research projects and going about with research work related to PM fuel cells.
Okay, yes.
Thank you.
Hello, good afternoon. Basically, I just want to ask one question regarding nowadays in our country, ONGC and Reliance Industries, they are putting out the gases from the well, right? Bore wells. They are gases.
Sorry, I can't hear you. Sorry.
Hello, you hear me now?
Yeah.
Yeah. Nowadays in our country, Reliance Industries and ONGCs, they are putting out the gases from the bore well, right? When the bore wells are empty, they are used to fill that bore well with water, right? And if they when they put out all the gases and they put the nitrogen gas to fill that gas, is that impact the tectonic plates?
Is the what? Sorry.
Is that if the bore well is again filled with the nitrogen gas, if it is locked with the nitrogen gas, it impact the tectonic plate?
So I didn't catch that. Sorry.
Hello.
The last part of the question. Sorry, I didn't catch.
Basically, when we exhale the gas from ground, right?
Okay.
We use the bore wells to exhale, right? And when the bore well is empty, no gas is left behind, then the multinational companies use water to refill it, right? For the level. I just asked, if the bore well is empty and we use nitrogen gas to refill it, right?
Yes. So the idea is to use gas reservoirs or gas to put hydrogen back in. So you just replace methane with hydrogen. And quite often what they have done is use CO2 to purge it out. So one of the ways of extracting gas in shales is to push through with CO2. So there might be CO2 in there already. So you're already storing CO2 as part of the extraction process. Or if there's methanes come out, then you can put hydrogen in. It all depends on the nature of the reservoir. Okay, where it is. The ones that fill with water, you tend to inject supercritical CO2 that will force the water out. Okay, so the oil reservoirs where you're storing CO2, for instance, you'd actually use supercritical CO2, pump it down, and use the pressure of that gas to force out whatever's in there. Okay, so you just use the gas pressure to force out what's in there.
Good afternoon, Professor. I have a doubt related to microwave chemical processing. There should be a two frequency of magnetron can be used for the microwave chemical processing, 915 and 2450. In homemade, we are using 2450, but industrially they can use 915. So which one is so efficient regarding with the drying process as well as extraction process? Because basically I am a food technologist. So I am using that microwave for the extraction of bioactive chemicals and some other methods. So which one is best frequency for extracting the bioactive compounds from the food waste? Whether it is 915 or 2450, which one is best?
So, which one is best, microwaves or?
Frequency range. That is, in homemade microwave, we are using 2450 megahertz. In industrially, they are preferring 915 megahertz. So, which one frequency is best for the extraction of biologically active compounds?
Oh, I don't work on the biomass stuff, only on heavy oil things. So the microwave processing I do is catalytic upgrading. So I do inorganic reactions. My colleague, John Robinson in Nottingham, has done lots of work on microwave pyrolysis of biomass to make precursors for fuel and also for fine chemicals. Also looked at lignin, microwaving of lignin. So I haven't done the work on that. I use microwaves for more inorganic reactions. But if you're interested, I can put you in touch. Okay.
Thank you. Thank you.
Thank you, participants. If you have any other questions, you can meet him personally during the break and ask him. Thank you, Professor Sean Rigby, for such an enlightening talk. It was a pleasure listening to you. It's a matter of great pride to have a person like you with tremendous achievements with us. Thank you, sir. I would like to invite our beloved principal, Dr. Anand Achari, to honor Chief Professor Sean Rigby with a certificate and a memento. Sir, please. The memento that is presented to our chief guest is a pencil sketch which is drawn by our own PG student Ambrish. The memento that is presented to our chief guest is a pencil sketch which is drawn by our own UG student Ambrish. Thank you, dignitaries. Let's have a break for tea now. Before that, I would like to invite the dignitaries and the external participants to the front for a photo session. I would like to invite the dignitaries and the external participants to the front for a photo session.